So our equilibrium equation for bonds is that partial differential equation. The modeling approach to bonds is similar to what we did with stock, creating risk-free portfolios and seeing what that tells us about what differential equation prices must satisfy. In the same way that with stock options, we have a differential equation, we need a boundary value. The boundary value determines the different values of the options. It's the same with our various zero coupon bonds. Namely that all of the prices of our zeros satisfies that differential equation, but they all have different boundary values. Namely, the 10-year zero has a value of 1 at time 10. The 20-year zero doesn't have a value until time 20, and so forth. So by instituting those boundary values, they act just like the exercise value of the options on stock. They give us a terminal point, and because the differential equation only tells us how the price moves, we need a terminal target value, and then that's what determines a unique price for us. The final comment in this section, in this module, has to do with delta gamma approximation for bonds. We looked at that in the market maker section. We looked in detail about how to do delta gamma type approximations for stocks and derivatives on stocks. We'll look at that more carefully here. So we have this stochastic process for the price of any derivative security on R, like a zero coupon bond. And what this process tells me is that the risk-neutral expected change in prices gives us the risk-free rate. And we've seen this before. The differential equation for the price of an option on a stock had as an implication that the expected return on every derivative security on stock, if you take that expected return in the risk-neutral measure, the expected return is always the risk-free rate. Well, we see the same conclusion here, no difference. We can write it this way, that the expected return over any period of time is the risk-free rate over that period of time. Another conclusion is that the delta gamma theta approximation for bonds holds exactly, or nearly exactly, if interest rates change by 1 standard deviation. Again, we saw this in the stock models. We saw that by virtue of the Black-Scholes equation, if the market maker sets up, when the market maker evaluates their total gain or loss position using a delta hedge, that their total gain or loss was 0 when the stock moved 1 standard deviation. So this is a related result. We're saying, in essence, that the approximation for prices using delta gamma theta, that approximation is exact when you have 1 standard deviation. And the derivation is, first of all, we write down what's the approximation formula for the price when interest rates and time move. Well, this is the delta term, it's the R derivative. This is the gamma term, that's the second R derivative, and this is implicitly the theta term, which is the T derivative. Right? So that's the approximation for the price using delta gamma theta. Now let's say that interest rates move 1 standard deviation, which means we have a drift and plus or minus 1 standard deviation. And now we insert it, we do the algebra, and we disregard all powers of delta t higher than 1. This is common practice now because in the limit they go to 0 quite fast. And we see that the approximate formula is equal to this expression. And if we look at this, it looks as if we replace the delta t with dt's, this is effectively the initial price plus dp. Namely that this second term is effectively dp. And so what we've concluded is that if we have an interest rate move that's exactly 1 standard deviation, the formula that we would use for approximating price using delta gamma theta will basically give us the exact answer, very close to the exact answer, because that approximation then reduces to a representation of the differential process that is obeyed by P.